of problems that pop up in it. Some are going to look, at least in instruction, a little bit familiar. Others will not. But we're going to spend a couple days on this. (13.4) is focused in on the double and the half angle identities. If you don't already have your identity sheet out, you should probably grab that, and you're probably going to want your unit circle as well. As of today, you are going to have every single identity in play. So now we're not just using the front of the blue sheet or the front and the top half of the blue sheet. We are now also bringing in the rest of it. As we go through this section, there are, like I said, a couple of different types of problems you'll see. Some will say find the exact value of. Now, anytime you get a situation where you're being asked to find the exact value of, well, anything for that matter, you're really going to want to start paying attention to a couple things. First off, if I give you something real basic, do not overcomplicate it. If I ask you for sine, oh, that is blurry. Better. If I ask you for sine of 135 degrees, what should you be telling me? Positive square root of 2 over 2. Because it's on the unit circle. Please do not lose that piece. But today, we're also going to be finding the exact value of some other numbers using our double and our half angle identities. Now, to be blunt, our double and our half angle identities are not going to be the favorite for this use. First off, the double angle identities. You can use a double angle identity to get it. You can find it on the unit circle. The double angle identities will essentially never be used to actually find a double angle unless you are in a situation where I, for example, give you what cosine of theta is and ask you to find cosine of 2 theta. Because then there's a formula that connects them directly. But I'm never going to give you an angle and say, use the double angle identity to find out what trig of it is. It's not necessary. The half angle identities, on the other hand, those are going to be ones that we might have to use the exact value for. Now, sometimes we won't, because the way that these ones work is that the angle I give you is half of an angle that's on the unit circle. Now, the nice thing about those is we're actually kind of limited on what angles that would be. Because if you think about angles on the unit circle, what's half of 0? 0. Isn't 0 directly on the unit circle? I wouldn't use this for. What's half of 30? 15. Is 15 on the unit circle? No, then I wouldn't use this. Half of 45? 22.5. Also not on the unit circle, but half of 60? 30. On the unit circle, I wouldn't need to use a half angle identity for half of this one. Half of 90, 45. So we're actually limited on what angles this will pop up on. We could do things like sine of 15 degrees using a half angle identity, but it's easier to use the sum or difference at that point. So instead, the angles you're going to see are going to be ones like this, where you're going to have a decimal involved more often than not. Because unless there's a decimal involved, half of 30 was 15. 15 degrees you could find much easier by doing two angles that subtract to give you 15. 0.5s on the other hand, there's no two angles on the unit circle that add or subtract to give me 67.5 degrees, and therefore I have to use a half angle identity. Now the half angle identities trip people up the most because of how they set them up. Half angle identities say cosine of theta over 2 equals positive and negative square root of 1 plus cosine of theta all over 2, which means the first thing we need to recognize is we need to recognize 67.5 as a fraction. Yep. Yes. But that's not what I said. It's 135 over 2? Yes. It's not kind of how you said it, but yes. So what over 2 is 67.5? That's the first thing you have to establish. Easiest way to do that, multiply that by 2. You would have gotten 135. Because you know it's going to be an over 2. Here's the challenge with what goes into this, using this one. Here's the thing that trips people up the most. In the identity, what is theta? The 135. It is not the 67.5. In the identity, it has to be that. Far too often, people start putting the 67.5 into the identity, which causes issues because you still don't know cosine of 67.5. If you did, you wouldn't be using the identity in the first place. So, theta is the 135, which means this is equal to a positive or a negative square root of 1 plus, here's the second thing that trips people up. Through this section, there are going to be times where I give you theta, and there are going to be other times where I give you cosine of theta. You have to be careful on which one I gave you. In this one, we do not have cosine of theta. I did not say cosine of theta equals and then give you a fraction. I gave you cosine of an angle that we don't know, in which you're getting theta out of it. So when you're plugging this in, you're plugging in theta. There are going to be other times where I give you cosine of theta, and you're just plugging in that as a fraction. The cosine symbol, or the cosine operation, disappears. We're going to get more of that tomorrow, but you just have to pay attention. Is this a situation where I'm plugging in theta or I'm plugging in all of cosine? Today it's going to be theta. Okay. From here, it's just a matter of simplifying. First thing I could simplify is what is cosine of 135 degrees? Negative square root of 2 over 2. You cannot leave a fraction inside of a square root and call it simplified. So, we've got to get rid of the fraction inside the square root. To get rid of the fraction inside the square root, I need to start by working with the fraction itself. In this fraction, first thing I have to do is deal with that numerator. That numerator is adding a whole number and a fraction. In order to add fractions, need a common denominator. The common denominator between those two would be 2. 2 over 2 minus square root of 2 over 2. Technically it's plus a negative, but that's the same thing. Okay, so I get that common denominator. Now I subtract my fractions. Now when subtracting my fractions, 2 minus square root of 2, do those go together? No. 2 minus square root of 2 all over 2 all over 2. That's another thing that people tend to miss, is I've still got a complex fraction here, and it oftentimes is going to be an over 2 over 2. Okay, to divide fractions. Multiply by the reciprocal. Now there's going to be a little cheat that we can work with here, because 2 minus square root of 2 all over 2, it was divided by 2, which is 2 over 1. Flip that fraction, becomes 1 over 2. And to multiply fractions, you multiply straight across. So I get 2 minus square root of 2 all over 4. A little trick, a little shortcut that you're going to have in the end. When you have a situation like this, those are essentially just going to get multiplied in your denominator. Okay, now I take the square root of the fraction. To square root a fraction, you square root the top, you square root the bottom. I get the square root of 2 minus square root of 2 all over the square root of 4. Can't leave a square root in the denominator, but thankfully, right now my denominator has the square root of 4, which is a nice perfect square. 2. And we're almost done. Yeah, these ones are a process. Any thoughts on what we still have to do, probably? Guesses? Show that it's what? Nope. Determine if it's positive or negative. So, we cannot have the positive and negative left on the final answer. To determine if it's positive or negative, think about the original problem. The original problem was cosine of 67.5 degrees. At an angle of 67.5, should cosine be positive or negative? Use your unit circle if need be. At that angle, cosine should be positive. Because at 67.5 degrees, we're somewhere around like here-ish. And in this quadrant, all of the trig are positive, actually. But cosines are x values, and they are positive. These problems, at no point become particularly pretty. Our final answer is the square root of 2 minus the square root of 2. Make sure that that first square root is big enough to include this little square root all over 2. If you're like, I'm not sure I did that right, you can always double check using your calculator. Cosine of 67.5 is that grossness. Square root of 2 minus square root of 2 all over 2. Uh-oh. All over 2. Same ugly grossness. It's kind of hard to see. You do have to make sure that you get your parentheses in the right place, though. Because if you don't put parentheses in the right place, it's not going to put it into the calculator nicely, especially if you've got an older style calculator. I got one of the fancy ones that works out nicely. If I wanted to type into like a TI-83, it would do square root, it would open a parentheses, I'd have to do 2 minus square root, it would open a parentheses, I'd have to do a 2, close that square root, close the other square root, and then divide by 2. So, if you're wanting to check your answer, just make sure you're typing it into your calculator correctly, otherwise it's not helping you. Don't mind me, I'm just changing my mind on what it is that I'm doing for examples today. Try this one out on your own. subtract the numerator and keep the common denominator. You don't need that much sugar. I stand by my statement. Why is it negative? Sign is negative there, but the angle is 315. The angle is 157.5. Yes, it is turning into that one. No, it is not negative. Correct. But the original angle wasn't 315. The original angle was 157.5. So here, which means our final answer is why is it minus negative? No, I don't know either. That's why. Double check the identity. Grab the blue sheet numbers. The identity that goes here. Cosine. Okay, I'm seeing two common themes pop up with mistakes that people are making. First off, 157.5 people are doing beautifully and recognizing that that is 315 divided by 2. Sweet. Positive and negative, square root 1, and then they're recognizing it's minus, and then here's where the problems arise. On the identity, what goes inside the identity? Cosine of theta. Yes, I know this is sine. I don't care. The identity says to use cosine. Cosine of the 315 degrees. Positive, negative, square root, cosine of 315 is? Root 2 over 2. Not a negative root 2 over 2. That would be sine of 315. Doesn't this look a lot like the last one we did? Yeah, you get the common denominator that's currently 1 over 1 becomes a 2 over 2. When you subtract, you get 2 minus square root of 2 all over 2 all over 2. Shortcut I told you is what's going to happen with those two 2's? They're essentially going to multiply, because when you multiply by this reciprocal, it becomes 1/2. And it always is going to end up just multiplying by the denominator. So I get 2 minus square root of 2 all over 4. And people are doing beautifully to get to here. The second mistake I'm seeing is this positive or negative. Should it be positive or should it be negative? Positive. Because remember, your original angle was not 315. Your original angle was 157.5. 157.5 is over here. We're talking about sine of it, and sines are the y values, which are positive. So, positive, isn't the exact same answer as the last one? Yeah. So you will find that many of these actually end up being the exact same answers. The only difference that you're going to find between these ones is it positive or negative at the beginning? Is it a plus or a minus sign inside? Because the only other times that these end up being different and getting you different numbers, things that are not square root of 2's, is in situations where it's not the 45, 135, 225, 315 degree angles getting divided in half. But if I divide any of the other angles in half, I will have one of two situations pop up. Either it will be an angle on the unit circle, like 120 getting divided by 2 is 60. I don't need to do a half angle identity for that. The other option is like a 30 degree angle divided by 2. 30 divided by 2 is 15. Which is easier to do based on what we've done the last couple days? These identities or these ones? These ones. Don't get me wrong. You can do sine of 15 degrees using this. It will work out beautifully. You will get something that doesn't look like the answers that we got on Friday, because of the fact that it simplifies down differently. And you will get something more along the lines of two minus square root of 3. I put that square root too big. All over 2. And so it'll look a little bit different, but for the most part, it's still easier to do a sum or a difference identity at that point. Those are really the only times you're going to get something that looks different. Okay, technically with one more exception. Tangent. Because the tangent identity looks different. It's more complicated. We established on the previous problem that this is 315 getting divided by 2. Therefore, we have a positive or negative square root of 1 minus, it's still cosine of 315 over 1 plus cosine of 315. Cosine of 315 was a positive square root of 2 over 2. When you're doing tangent, there's going to be a lot more involved in simplifying it. You're going to need the common denominator and subtract and add the fractions. Common denominator is going to be 2. This is 2 over 2. So I get 2 minus square root of 2 all over 2 all over 2 plus square root of 2 all over 2. Ugh. How do we divide fractions? Multiply the reciprocal. So 2 minus square root of 2 all over 2 is getting multiplied by 2 over 2 plus the square root of 2. To multiply fractions, if there's a plus or a minus, you have to distribute unless you notice something else first that'll make it where you don't have to. That 2 and that 2 will cancel. Positive or negative? Square root of 2 minus root 2 over 2 plus root 2. Unfortunately, I cannot leave a square root in the denominator. I cannot leave a fraction inside a square root. I got a lot of issues here. I have to rationalize my denominator before I ever think about taking the square root of the fraction itself. Which means I'm multiplying both the top and the bottom by the conjugate of this. Making my little note to self, multiply by the conjugate of the denominator, which is 2 minus square root of 2. Remembering that I've got a lot of parentheses technically going on here. I'm left with a very large square root. 2 times 2, 4. 2 times negative root 2, negative 2 root 2. Negative root 2 times 2, negative 2 root 2. Negative root 2 times the negative root 2, positive root 4 or positive 2 over 2 times 2, 2 times negative root 2, sorry, negative 2 root 2, I should say. 2 times root 2, positive 2 root 2. Positive root 2 times negative root 2, negative root 4 or negative 2. In the denominator, we're going to have some canceling happening again. In the numerator, I've got some combining like terms I can do. In the denominator, I do as well now. Four plus 2 is 6. Negative root 2 minus 2 root 2. Sorry, negative 2 root 2 minus 2 root 2. Negative 4 root 2s. All over 4 minus 2. 2. You don't look impressed, Daddy. I can't blame you. Can I simplify the fraction? Yes, and that's the way you're going to want to go, because otherwise you're going to have to rationalize the denominator after you split the square root. Hard pass. Yes. If all three of these divide by something, do that. Positive or negative, square root of 3 minus 2 root 2. Technically all over 1, but I don't care about the all over 1. Especially since it's a square root of 1, which is still just 1. Final thing, positive or negative? Why?
Because all of tangent on 157.5 degrees is negative.
The key thing is you're looking at the 157.5 degrees. You're looking here. And in this area, tangent is negative. Make sure your square root is still over all of that. Yay to ugliness. Y'all don't seem to be on the same page. Not yay to ugliness?
It's not even math.
It is still math. I promise you, it is definitely still math. 100% still math. Okay, there is one more problem I need to show you today. You are going to see verify and simplify problems come up. Verify is going to be more common with these identities. To verify with these new identities, you're still following the same rules that we've been following through verify. What is the first thing you should always check?
Angle is the same.
That the angles are the same, are they?
Yep.
No.
Oh. No, that's theta, 2 theta.
I've got theta, and in the middle I've got 2 theta. Anytime you come across a 2 theta, 2 thetas you should be looking at your double angle identities. Now, thankfully, this is a sine identity, which gives us limited options on what to do with it. If it's a cosine identity, you have to make a decision on which of these 3 makes the most sense in the problem. All 3 of them will get you there. You just have to look at the problem and say, is all of the problem cosines? I should probably do this one. Is all of the problem sines? I should probably do this one. Is it a mixture of sines and cosines? Maybe that one's best. If it's sine, you've only got one option. So we do that first. But this is squared, which means when I'm replacing it, remember that sine squared of something is just sine of that something in parentheses squared. So that means this is 2 sine of theta cosine theta in parentheses getting squared. Now that seems like a very scary thing to put on there because now I've got to square something. But do you notice there's not a single addition or subtraction in it? Mm-hmm. To square something without addition or subtraction in it, you just square all the pieces. When there's addition or subtraction, you have to multiply it by itself and you're going to have to FOIL things out. In this case, you will not have to. So, 2 squared, sine squared, cosine squared equals cosine to the 4th theta. From here, you've got some options on where to go. There's not necessarily a right or a wrong answer. I personally notice over here's just cosines. Over here's got a lot of cosines. In fact, there's cosine squared on both of these. I personally would factor. Out of these, I can factor both the cosine squared out, but also a 4. Because sine's not on both. But 4 cosine squared's on both. Factoring 4 cosine squared out of 4 cosine squared, 1. Factoring 4 cosine squared out of 4 sine squared cosine squared, sine squared. 1 minus sine squared is one we've seen a lot. It's cosine squared. If you're not sure where that's coming from, ask me during work time here and I will be happy to show you. But then we get 4 cosine to the 4th theta equals 4 cosine to the 4th theta. So, the rules still apply in the same way that they always have for the verified problems. You just have more things to look out for are the angles the same.